This structure is mostly air, yet this one survives impact that solid metals fail. This panel looks thin, yet this one carries load a solid slab cannot. This column is hollow, yet this one resists collapse better than a solid one of the same weight. Nothing here works because engineers discovered stronger materials. Nothing here works because of new chemistry. It works because modern engineering stopped treating force as something to resist and started treating force as something to manage. Most people believe strength comes from thickness, more material, more mass, more solidity. That belief feels obvious, it feels safe, and for most part of human history, it was correct. This video is about why that intuition breaks in modern engineering. Not about materials, not about tricks, but about how distributing force over time and space produces strength that solid structures cannot achieve. For thousands of years, human built structures dealt with slow forces. Walls carried weight, beams supported roofs, bridges resisted gravity. When forces arrive slowly, thicker structures perform better. More material spreads the load, cracks form gradually, failure gives warning, and castles, stone columns, massive foundations were built for this world. In that context, solidity meant safety. But modern engineering does not live in that world. Modern systems face impact, acceleration, vibration, and shock. Energy now arrives suddenly. Under these conditions, solid structures do not fail gracefully. They store energy until they release it all at once. This is why solid designs often fail catastrophically instead of predictably. To see how engineers solve this problem, we start with a structure that looks obviously weak: metallic foam. A block of metallic foam looks fragile, it feels light. It's mostly empty space with thin metal walls surrounding air. If strength came from thickness, this structure should collapse instantly. Now, compare it to a solid block of the same metal. Under impact, the solid block resists briefly. Stress builds internally, cracks form, and the failure happens suddenly. The foam, however, behaves differently. The outer cells collapse first, then the next layer, and then the next. The block shortens instead of snapping suddenly. Nothing magical is happening, no hidden reinforcement, no exotic chemistry. Each small cell deforms slightly. Energy is absorbed locally. Force spreads across space instead of concentrating in one place. The solid block has only two states, intact or broken. The foam has many intermediate states. This difference is the foundation of modern impact resistant design. At this point, it is easy to reach the wrong explanation that lighter structures work simply because they are lighter. That explanation sounds reasonable, but it fails when you look at honeycomb panels used in aircraft and spacecraft. These panels consist of thin skins bonded to a hollow core. The core is mostly air. A solid plate of the same weight bends easily. The honeycomb panel remains stiff. If mass were the key variable, both should behave similarly. They do not. When a panel bends, stress concentrates far from the center. The honeycomb core does not carry load directly. It pushes material outward. By separating the skins, the structure resists bending without adding weight. At the same time, thousands of internal cell walls deform slightly, sharing load across the space. This is not material removal, it is material relocation. Weight reduction is not the mechanism, geometry is. Once engineers understood that geometry mattered more than mass, they began to rethink what strength actually means. Now, look at the modern day cars. A car that does not deform in a crash is not strong. It is dangerous. In a collision, motion must stop. The only question is how fast. Rigid structures stop motion instantly. That creates extreme acceleration, which transfers directly to the occupants. Modern cars are designed to fail first. Crumple zones are hollow, folded, and segmented deliberately. When impact occurs, metal collapses in a sequence. Each fold absorbs energy. Each millisecond matters. By increasing the time over which motion stops, peak force is reduced. This is not weakness, it is controlled sacrifice. Here, strength is no longer defined by survival, it is defined by injury reduction. Strength is not resistance, strength is force shaping. This idea does not depend on scale or industry. It appears again in some of the lightest materials ever engineered. Aerogel looks very unreal. It is over 90% air. It feels like frozen smoke. Yet, aerogel lattice blocks can support loads thousands of times their own weight. They do not rely on solid mass, they rely on paths. Load does not move through volume, it moves through connections. In aerogel lattices, stress travels along thin struts. Each strut bends slightly. Each deformation absorbs energy. There are no large continuous surfaces for cracks to race across. Failure has no single direction to accelerate. Different materials, different scales, same outcome. The behavior is structural and not material specific. Once this pattern is clear, engineers can design structures that outperform solid ones even under pure compression. A solid column under compression fails by buckling. Once bending begins, collapse is sudden. Architected lattice columns behave differently. Compression is redirected into angle load paths. Local instability appears first, then secondary paths engage. The column shortens gradually instead of snapping. No single element carries the entire load. Instability is delayed by design. This is where the governing principle becomes explicit. Distributing force over time and space is more effective than resisting it all at once. The single rule explains metallic foams, honeycomb panels, crumple zones, aerogels, and lattice columns. Failure is not eliminated here, it is choreographed. Failure is unavoidable. Energy must go somewhere. If engineers do not design where it goes, physics will decide. And physics chooses the most fastest, most destructive route. Modern engineering designs slow failure. A lattice buckles cell by cell, a foam crushes progressively, and a crumpled zone sacrifices structure in a controlled sequence. Nothing detects overload, nothing decides when to fail. The geometry already knows how. Failure is not an error state here, it is the mode the system is allowed to enter safely. This is why the most trusted systems do not try to avoid failure, they design it. What I've seen here isn't the trick. Metallic foams or honeycomb panels or the crumple zones or the aerogels or lattice columns are all across different industries, different scales, and are all different materials. Yet the same logic keeps appearing. Force is not resisted, it is redistributed. Force is not prevented, it is shaped. This pattern shows up too consistently to be a coincidence. Engineers are not inventing new ideas every time. They are reusing a small set of structural behaviors because physics keeps rewarding the same solutions. That is why modern engineering starts to look familiar once you notice it. Hollow, segmented, directional, and quiet. Not because designers copy each other, but because reality keeps selecting the same answers. This is not one principle, it is one instance of something broader. Once you recognize that, machines stop looking complicated, they start looking inevitable. And the more extreme the environment, the fewer design ideas survive.